In this video, we're asked to find the Maclaurin series for f of x equals sine of x. Well, I'm going to start by taking some derivatives. So the 0th derivative, the original function, is just sine. F prime of x, of course, is cosine. We know how these trig derivatives behave, and very nicely. And here, when I get to the 4th derivative, we've looped back around to the original function, and we know this behavior of sines and cosines, that these derivatives will just keep looping around. So I'm going to think about my Maclaurin series, right? I take the nth derivative, I plug in a 0, I divide by n factorial, those are my coefficients, times x to the n power. All right, so this shouldn't be too bad. I need to evaluate all my derivatives at 0. And it won't take me too long to figure out what's happening. And I see what's going on. All of the even derivatives, including the 0th, the original function, well, there's 0. The odd derivatives are going to alternate between a 1 and a minus 1 as this continues to loop around. So if I just think about this, I have f of 0 plus 1 over 1 factorial times x plus, well, 0 times whatever, minus 1, and let's see, that's the 0th term, the first term, the second term, this is the third term, so over 3 factorial times x cubed, plus 0, plus 1 over 5 factorial x to the 5th, so on and so forth. All right, so let's see. The zeros I can get rid of, and I know I just have the odd powers. And I know they alternate in sine. I know I'm always dividing by a factorial, so I know exactly how all the terms of this series will behave. So I want to write it down as a series. And so when I think about this, I will always have a minus 1 to the k as giving me the sign, right? Because I raise a minus 1 to the 0 power, I get a positive. To the first, I get a minus. And that continues throughout. And I'm always dividing by an odd factorial. So 2k plus 1 factorial. Because when I plug a 0 in, I get 1 factorial. When I plug a 1 in, I'll get 3 factorial. And then finally, x raised to that same 2k plus 1, that odd exponent. And there's our Maclaurin series for sine, written out to the 7th degree Taylor polynomial and expressed as a series. And while that's all we were really asked to do, I feel like we should also talk about where this series converges. All right, so I'm going to use the ratio test. The ratio test here, I'm going to test for absolute convergence, so I'm going to just imagine getting rid of that minus 1, because when I put it in minus 1, all of the terms would be positive. So the variable expression needs to be an absolute value. Oh, and I need to be thinking about the n plus first term, so I need to replace that k with an n plus 1, and it's not too hard to find out that I'll make that actually a 2n plus 3. Same thing goes on with the factorial. And I need to divide by the nth term, so I'll plug an n in for these k's, and I'm going to multiply by a reciprocal because I know I'm dividing. All right, this limit's not too hard to deal with. I have 2 more of the absolute values of x on top than I do on the bottom, so I have the absolute value of x squared, which I could just write x squared, but it's not going to cost me anything to leave it there. And I'm dividing by, well, what's left over when I cancel out the common factors would be 2n plus 3 times 2n plus 2. Well, the top of the fraction is a constant as n goes to infinity, so this goes to 0 for all x. Well, that's super important because that's always less than 1, which means this Maclaurin series converges absolutely for all x. I always like to say it converges absolutely everywhere.